Oh dear, all these people standing. There's some seats in the front row here. It's a pleasure to be back in Princeton here at the Institute. I and my wife, who's sitting back there, came to the Institute in the medieval period. It's that 1955, and most of you weren't even thought of. But even so, it was just too late for me to meet either of my two heroes, Albert Einstein and Hermann Weyl. They both died in 1955. Einstein died, and there's more to say. Weyl was in Zurich, Einstein died here, but I came just too late. But I did have a chance of seeing Hermann Weyl at the Amsterdam International Congress in '54. When I was a graduate student, I went and heard him talk about the great works of Sayre and Kodaira, which received field medals. So I had an idea of what he was like. Einstein I never met, but his reputation here, of course, lingered on. Now, the title gives you, this is going to be sort of somewhat of a philosophical talk, as you can see, but it also has implications for the actual work in mathematics and physics that I'm interested in doing. Because it depends on what your motivation is. Hermann Weyl once said, famously, that in his life he searched for truth and for beauty, but if in doubt, he chose beauty. Now, most mathematicians would think that was terrible. A mathematician is ultimately the man who searches for proof above all else, proof and truth. But that's a misconception. Hermann Weyl knew what he was saying. And I think what he was saying is that truth is something you never know whether you got it. You're searching for it. It's ultimate goal. What you got may be a partial truth, halfway to the truth. How do you know it's not going to change? On the other hand, beauty is something you immediately perceive. It's your personal reaction. Nobody can argue it. If I say I see a blue colour over there, you can't tell me it's green. So that's one thing. Secondly, I think you can say it this way around, that we mathematicians and scientists are searching for truth. It's our goal. But beauty is our guiding light that leads us there. And that's the thing that it leads the individual a particular direction or another one, and whether he's successful or not is how clever he is at using his intuition to follow a particular path. So Weyl was very serious about that. I'm told if I press a button here, something happens. Oh yes. Well, but there are meant to be some equations there. What happened to the equations? Oh dear, dear. Oh, this technology is not always as brilliant. Maybe it'll appear on the next page. Let me just see. No. Oh dear. I'm let down. Well, we'll have to put out. I'll tell you what the equations are. First of all, Hamilton was another of my heroes. As you know, he was a great mathematical physicist. In his work on classical mechanics and the Hamiltonian provided the foundation for quantum theory subsequently. But many people think that his invention of quaternions was a byproduct, it's a dead end. And I've read books which say, they called it, chapter on Hamilton, the Irish tragedy. The man, the great man, mathematical physicist, who had tremendous impact in his time, but then he discovered these stupid things called quaternions. He spent his time fiddling around with equations. He wrote them on, inscribed them on a bridge, you remember, this small marvelous story. He put them on the bridge, and what a waste of talent. He should have been stuck. Well, that's quite often what happens to great men. They have a vision of the future which the other people don't share. And if you wait and see what's happened to mathematics and physics subsequently, well then, lots of things have happened to justify Hamilton's belief in quaternions. Now I can't, it's a pity the equations disappeared. I don't know what's happened to it. Secretary this morning worked very hard. She put it all up, but it disappeared. Must be some kind of gremlin in the system that senses out the equations. Well, you know that Hamilton invented quaternions, and after the complex numbers where you have 1 and I, he added j and k. He was actually searching for 3 dimensions. He was really interested in applying algebra like complex variables in 3 dimensions instead of 2. That was his goal. It wasn't just algebra. His goal was to do physics. But he found, to his surprise, that you couldn't stop at 3. You had to do 4. J and k came together. The whole system closed beautifully. And that's when he wrote it down on the bridge. He suddenly had this inspiration. The system closed. Quaternions were born. And in his book, much of his books were unreadable, I have to say. But that genius sometimes is like that. He wrote down this equation, which I've got in front of me, which you can't see. And the equation is I d by dx plus j d by dy plus k d by z squared is minus the Laplace operator.
You do have a blackboard.
No. I can project myself just as well as backward. Well, that equation, he said, with great precision, this was in 1840 or something like that. This equation must have far-reaching repercussions in mathematical physics. That was a century before Dirac, or large parts of the century before it was used. But he discovered the Dirac operator, and he knew it was important in mathematical physics. He wasn't saying this trivially. He felt in his bones this must be important. At the same time, the quaternions, of course, essentially involved spinors. He invented spinors. The SG2 group is the group of unit quaternions. Practically everything physicists now do with bread and butter was actually pioneered by Hamilton. He knew what he was doing. His contemporaries thought he was wasting his time, but most of you now know better. So he is the first of my heroes. Now, next of my heroes, who's, again, his equations have been somehow eliminated, is William Clifford. Very remarkable man. Unfortunately, he died young of tuberculosis, but he invented many things. Not all of them have his name attached. He certainly invented Clifford algebras, which are now very popular, very important, and in particular, the Clifford algebras lead to the system called the octonions. After Hamilton did quaternions, because there was flurry interest, other people trying to go beyond quaternions, and the octonions emerged from that, and the Clifford algebra also emerged. So this was the impact of Hamilton on his contemporaries, was to push algebra in this direction. Now, Clifford was a very man of wide interest. And in particular, he discovered what is now called Hopf vibration. Again, terminology is always inappropriate, inaccurate. Hopf did not discover the vibration. Clifford did. To modern readers, it's the vibration, the fibre of the 3-sphere over the 2-sphere with the circle as fibre. It is a fundamental piece of topology. It's the beginning of modern theory of fibre bundles. It lies behind the Dirac quantization of electric charge. It's a tremendously important piece of topology. He was the first who died, and you can see a beautiful picture of what he drew, which was actually the stereographic projection of this into space. He also had thoughts, which are perhaps only vague thoughts, that nature of matter was simply the curvature of space. He threw it in an offside remark. He said that's how it should. So again, very percipient. He was say, a remarkable public speaker. He was much in demand as a public speaker on all topics, not just mathematics or physics. He was one of these lecturers that people rush in to hear. But I say, sadly, he died as a comparatively young man. Now I hope that I hope Einstein has been cancelled as well. Thank goodness. So I don't know all these by heart. But anyway, let's go through them, because this gives you something of the philosophy of Einstein. I want to know how God created this world. I'm not interested in this or that phenomenon, in the spectrum of this or the other element. I want to know his thoughts. The rest are details. Quantum mechanics deserves much respect, but an inner voice tells me that it is not yet the real thing. The theory gives much, but hardly brings us to the mystery of the old fellow. At any rate, I am convinced that the old fellow does not throw dice. That's a famous quotation. And then the next one. These are originally given in German. If you know German, you will know the better version of this. My colleague Raoul Bott always used to quote the German. The Lord is clever, but not malicious. And finally, one you appreciate, if God created the world, it was clearly not his main concern to make it such that we understand it. His thoughts are very well worth pondering over. And then the next couple of Einstein quotations are also good. The most incomprehensible thing about the world is that it is comprehensible. And the more you think about that, the more you ponder its meaning. Why is it that we find equations that seem to describe the world? Where do they come from? It's the ultimate mystery of the world, in a sense. And the more we go on, the more beautiful the equations to come, the mystery just deepens. And the last line, put a casual remark, don't worry about your difficulties in mathematics, I can assure you mine are much greater. Well, that was a modest statement of a great man. Now, a very opposite extreme from Einstein in his mathematical work, but somebody who was also close to me, Trinity College, Cambridge, was G.H. Hardy, the number theorist. And his quotation from his is, the mathematician's patterns, like those of the painters or the poets, must be beautiful. The ideas, like the colours or the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. He was an ultra sort of proponent of beauty. And he meant it, and I think many people have sympathized. Hardy and also Hermann Weyl, Einstein, frequently refer to God, by the way, in their statements, you've seen. And it's not quite clear what sort of God they're referring to. Einstein refers to the God, the old fellow, malicious, and so on. I don't think he belonged to any orthodox creed. I mean, his God was a mathematician or a physicist. He wasn't anything else. And Hardy, even less. Hardy was a notorious atheist. And they used to say that there is no God, and Hardy is his prophet. He also played tricks with God. He well known when he crossed the Atlantic, which was rather rarely in those days. He was worried that the boat might sink. So he would, before going off, he would always send a telegram to Littlewood saying, "I have solved the Riemann hypothesis." On the grounds that God existed, he wouldn't let Hardy gain the glory for this by sinking. Everybody else thought he'd proved it. So it was an insurance policy, and he arrived safely. So he insured himself against the God that he didn't believe in. It's nice sort of paradox. Now, next I give a lot of small quotations, garnered over the centuries. Here we are. Numbers rule the universe, Pythagoras. God is a geometer, Plato. God created everything by numbers, Isaac Newton. The great architect of the universe now begins to appear as a pure mathematician, James Jeans. And Bertrand Russell said mathematics possesses not only truth, but some supreme beauty. The book, it might be a spoof. Sometimes these great things are spoofs. There's the Clifford algebra. There's the division algebras. And there's the Hopf invariant one, thing which I ended. And I say, Frank Adam and I wrote a little paper which extended the results from prime 2 to other primes, sort of technical exercise. Now, most of my life, a large part of my life, at least the first 40 years of my life, it seems a short time to me, was devoted to this sort of topic. K-theory, theory of vector bundles and so on, the Dirac operator, which we sort of rediscovered ourselves. Although I went to Dirac's lectures, I didn't really pay much attention then. And later on we discovered that it has marvellous importance in mathematics. The famous Bott periodicity theorems, and for those of you who didn't know, there's my great chum and collaborator, Raoul Bott. He's still looking down on us from up high. And there's a connection which Hinsberg and I worked out, which connects K-theory with homology. It has the form of a spectral sequence. Those of you who know about these things, it starts from the cohomology, and by a sequence of iterated steps, gets you not to the K-theory as a whole, but to the associated gradient bit. This encapsulates, I said, about 20 years of work, with a lot of repercussions in geometry, topology, manifolds analysis, and that little bit about the Adams-Hopf invariant theorem was one of the consequences. Now, I want to move on to something a bit beyond that, but we'll see where it comes in. This is the famous magic square, which I only really learned about a few years ago when I collaborated with a colleague on some particular problem, but it's known to all the experts in this field. It's due to Freudenthal and Jack Tietz, various forms. It's about the division algebras. The AI stands for the real numbers, complex numbers, quaternions, and octonions. And here is a 4x4 symmetric matrix, which says to be built up out of the tensor product of AI times AJ. So if you look in the, well, try to use the laser pointer, it might damage things. The top row gives you, this is actually this Gothic stuff because these are Lie algebras, but you can put in groups if you like. You have the real orthogonal group with three unitary group, symplectic group, and then you have first the exceptional group, F4, which plays the role of the 3x3 matrices over the octonions. The next row is supposed to correspond to the complexification of the one before. So, for example, if you take the predictive planes associated with those four groups, the next row are actually the complex algebraic varieties, which are complexifications of the real planes. The real predictive plane, due to the octonions, has a complexification, which is actually a nice algebraic variety, which is a homogeneous space of the exceptional group E6. And some miracle, as you go further down, you get E6, E7, and E8, where the exceptional groups stop. And if you wonder what happens to G2, well, G2 comes in because it's the automorphism of octonions themselves. So all the exceptional groups are entirely captured by these division algebras and their relationships. So even if they're limited, they don't go to higher dimensions, the octonions generate this remarkable group of exceptional Lie groups. So we have the classical groups and we have the exceptional groups, finite in number, but very, very beautiful things. For example, not only are these exceptional groups, but they're also intimately related to the regular solids in ordinary space. Things like the icosahedron are intimately related to E8. So they are fascinating things in their own right, even if they are exceptions. And I've written at the bottom, one problem. This is another problem in topology, which is a kind of grandson or something like that of the Hopf problem, and has been solved by Mike Hopkins and his collaborators in a paper of about the same length as the Frank Adams paper. And they've solved this, which is regarded as a great coup in topology, with a slight drawback. They got a lot of, they know a list of things where have this invariant, which I won't define, exists, and they come in dimensions which are powers of 2. And the last one should be in dimension, well, powers of 2 minus 2, 126. I'm not quite sure whether that one exists or not. That's what they proved. Now, what I'm hoping to prove in a postcard shortly is that first, this is all can be done in one small postcard, and the last one exists, and they're all intimately related to this table. And I'm prepared to put a good sum on that being true. So this is really my by the way, the homogeneous spaces associated with these, their dimension goes up by powers of 2 all the way, both right and down. So if you start at the top, that's the projective plane of the reals, that has dimension 2. And you work your way down, and E8 one has dimension 128. It's rather remarkable. They're a beautiful collection of and they're all the models in the middle are homogeneous spaces of classical groups, but the ones at the end and down across the bottom are homogeneous spaces of the exceptional Lie groups. It's a very beautiful, and the magic is not a name that's been used by physicists recently, and there might be a relationship. I'll come to that. Now, next picture I'm going to show is to mention 3 people. One of them is in the audience. I won't embarrass him, but the other 2 are not. Some years ago, there was a meeting to celebrate Roger Penrose's, I think, 60th birthday or something like that. And I was a friend of Roger Penrose, so I was invited along. I think Alan Conn was there. And I said something at the time. I won't read it all to you because it's a bit long, but you can read it in the report of the conference. And I somewhat said this sort of thing, that the problem with physics is how to reconcile quantum theory with gravitation, and various different approaches. One is the sort of string theory approach, exemplified by Edward Witten. Then there is Roger Penrose's twistor theory. And then there is Alan Conn with his non-commutative algebra. They're very different approaches. Each of these are really first-class mathematicians, so you have to take their ideas seriously. And I said it was a bit like religions. In religion, there may be different kinds of religion. Each religion usually doesn't think much of the opposition. They're hostile, if not, and they have support followers. Now, people outside who are not religious at all say, look, they can't all be true, so they cancel each other out. Nothing is true. There is no. But there can also be people like me, sort of mystics, who believe each of them has some aspect of the truth in it, and the totality of truth is not seen by any one person, but is somehow the whole universe. I'm a mystic, and I hope that things have moved in my direction. Already it's happened that links have been established between all 3 of these approaches. So far, only tentative links, but I think that those links will get stronger. So that was a prediction I made 20 years ago, and we'll see how it goes now. Now, that's all the preparatory. Let's get down to some serious stuff. Retarded differential equation. Well, your heart groans when you see this, doesn't it? Well, let's take a differential equation involving one function of one real variable, and the only thing about it is that the value of the function at one point and a different point appear. So you have a retardation is that parameter r, which basically says that there's a signal from behind that you have to wait to catch up with, and that's very important in things like electrical engineering and control theory. You have to wait for delay or retarded information that reaches you. Well, a differential equation like that, which is called linear, can easily be solved, but go forward in time by simply repeated integration. If you know the value of the function over the interval 0r, you just move forward, integrate, get to the next step, and keep going. Eventually you get the function defined on the whole positive reals, and you go backwards. That requires that you can differentiate, and so you have to have data which is smooth, so you get a function going backwards in time as well. So you can solve this equation quite simply. But if you take an equation which is mixed, has both plus term and a minus term, it looks a bit troublesome, because for one of them you want to get the information going forward, the other one information going backwards, so what on earth do you do? Well, it's a serious problem, that one. I mean, this is not a trivial observation, and these equations, if you go into the books, literature, they're called mixed equations, and practically nothing is known about them. But people do say that these equations are more like elliptic equations, whereas this other one with only one-sided terms are like hyperbolic equations. You give initial data and you propagate forward in time or backward in time. The mixed one, you have to balance yourself at both ends, so you have to have some kind of boundary conditions at the ends to solve in the middle, hopefully a unique solution. Well, I mean, I say it's surprising. I went to a standard book on retarded differential equations I got in the library. I took it out. It'd been in the library for 15 years. I was the first reader. And what they said about mixed equations is about 1 page. So I want to say a bit more. Now, make the following observation, that differentiation by dt is the infinitesimal generator of translation. If you exponentiate this r d by dt, that is the same effect as shifting f by rt. So that's the first observation. And you need additional conditions which you could take to be x going to minus infinity or plus infinity. You might hope to get a solution. Now the point about the first observation, well, I'll come back to later, but let's go on a bit. If you have mathematics, addition and multiplication are the two basic operations of algebra, and they correspond in matrix language to, in geometry to the affine group. translations, you multiply and you translate AX plus B group. AX plus B group is the upper triangular group in SL2. Going the other way, I mean, you would have the lower triangular group. That requires you to add inverses to multiplication and addition. You're very familiar with that with modular forms, where you have a modular form which is not only invariant under things like that, which give you also has to invert under z goes to minus 1 over z. So if you add the inverses, you get the lower triangular ones, and then you get the full SL2 as a combination of the two factors. Now, do the following. Consider geodesics in the hyperbolic plane. Why? Well, let's see. Why should you consider? Well, I said that. Hyperbolic space in the plane can be modeled in a variety of ways. One of which is you think of it as an interior disk of a finite radius. And the geodesics in this model are just straight lines. They got what you get by going back to sort of space of 3 dimensions with signature 1, 2, taking planes through the origin, and so on. So this is the predicted picture. And in this picture, geodesics are straight lines, they're ordinary lines. But the metric is not what you think it is. It's given by the logarithm of the cross ratio. The cross ratio is you have 2 points. You join them by line. They meet the boundary in 2 more points. So there are 4 points. 4 points of a cross ratio. Something like the logarithm gives you how to define metric. This is the predictive geometry of the hyperbolic plane. Now, I think I must have missed a bit on the previous page. Yes. Now, the bottom bit at the bottom. If you consider a geodesic in the hyperbolic plane, a complete geodesic, it starts at one point on the boundary, which is the sphere of infinity, circle of infinity, and it goes all the way through as a straight line, actually, in this case, to the outside, another point in infinity on the circle where that line meets the circle. These 2 points, you can call them alpha beta on the circle, are the endpoints, and so the geodesic is entirely defined by those 2 points. So the space of geodesics in hyperbolic space is naturally parameterized by the product of 2 copies of the circle is the boundary, but you must exclude the diagonal because the 2 points mustn't coincide, otherwise you don't get a geodesic. So this is the space that parameterizes the geodesics in hyperbolic space. And now the relation of this with retarded equations and so on is that, you see, if you're on this geodesic, you can go forwards or you go backwards, that correspond to one or other of the retardation flows. But if you want the mixed equation, it's like defining the unique solution of the equation given the endpoints, and that is the geodesic. So the geodesic in hyperbolic space is a typical example of the unique solution you get for a mixed equation. Interesting, by the way, on this, while we're about it, you can think this is a sort of pure hyperbolic geometry where everything is governed by group symmetry and so on. But you can mess about with it. You can take the hyperbolic plane and you make a few bumps in the middle, rough it up. Then what will geodesics be? Well, the geodesics will respond to the bumps. They will go around them. But if the bumps aren't too violent, you should still get a unique geodesic. It has this point of infinity here, that point of infinity there. But on the way, it curves around, wobbles, and some ordinary differential equation you can probably solve will give you that solution. So this is a description of what happens with mixed equations, which survives perturbation by messing up the curvature. It isn't just purely group theoretical, but asymptotically you recover the group symmetry. Now that's a very sort of elementary remark, but I claim it has significant consequences for the ideas of mixed equations, because, you see, we're shortly going to move into the real world. Well, first of all, the use of hyperbolic geodesics rests on the simple Lie group SL2R. And this is, according to Dirac, much more beautiful than the limit of Euclidean space. If you take that circle and let it go to infinity, the geometry becomes geometry of Euclidean space. The group of symmetries of Euclidean space involves the rotations of the circle, and the translations is not a simple Lie group, it's a solvable group, in fact. So this depends on a parameter, which is the curvature of space. As the curvature goes to 0, the group degenerates into a solvable group. Exactly the same way in which the Lorentz group degenerates to the Galilean group in physics. And one of the quotations of Dirac, which if I have time, I will quote to you from his marvelous talk he gave in 1939, says that when that was observed, relativity came along, and the reason it was successful was because this group was much more beautiful. The semi-simple group was much more beautiful than the stupid Euclidean group, a Galilean group. Well, he didn't actually notice this observation. If he had done, then if Dirac had noticed that, he might not have developed quantum field theory the way he had. Because the difficulty with the quantum field theory of Dirac is precisely that the Dirac operator has both positive and negative frequencies. And so you constantly have this problem of mixing of the two types. That mixing of the two types is essentially the same phenomenon as I referred to up here. If you put it into the context of hyperbolic geometry, you understand what's going on, you can prove things. And my claim is that hyperbolic geometry gives you, it's a sort of course, it depends on introducing the curvature, scalar curvature, not zero. Then you can treat things like the Dirac equation much much better way than Dirac did. You might never have gone into the whole business of fluctuating vacuums and so on. But Dirac did not stick to his principles. He should have done, but he didn't. Well, now I put this particular, I'm going, history is always not what it seems. I didn't have this rationale quite so clearly in my mind when I wrote the paper with Greg Moore, which has not yet appeared, but those of you who are familiar with the archive will see that you can actually access it on the web straight away. And what we did in this paper was to speculate, I think that's the right term, on relativistic versions of delayed differential equations in fundamental physics, in particular the Dirac equation. You retard this equation, and then you see what the consequences would be, and the consequences are actually quite dramatic. And you can even try the same thing with the Einstein equations, which are a bit more tricky, but let's stick to the Dirac equation. So what Greg Moore and I did was we just, you introduce the retarded Dirac operator. Now, you might think that it's hard to introduce a retardation parameter in relativity theory, because after all, time is not defined. Any direction inside the light cone is time. How on earth do you do it? Well, you see, you go back and ask what Dirac did when he invented the Dirac operator. What was he looking for? He was looking for a first-order Lorentz invariant differential operator. And there was only one. It was the Dirac operator. But it required you to introduce spinors. And so he introduced spinors, and there begins modern physics, in some sense. Now, the people subsequently, I've read in the literature, that say that, well, the old boy got it right answer, but he was wrong reasons. You don't have to have a first-order operator. You can just as well by starting with a Klein-Gordon operator, second order, and you can still develop the theory, and so on. Poor chap, he was just lucky. Well, Dirac was much smarter than they were. The first-order operators are fundamentally different from second-order operators. Second-order operators are things like diffusion equations. First-order operators are like vector fields, and if you exponentiate them, they lead to differentiation. And so because there is a first-order operator which is relativistically invariant, you can define a universal Lorentz invariant retardation. There it is. This operator, Dirac operator plus some constant times the exponential of minus r times the Dirac operator is the Dirac operator retarded. And what does that mean? And what does the operator mean? All right, say exponential. Well, what it means is simply every plane wave can be decomposed into, every wave can be decomposed into plane wave. If it's a physical wave, then it shouldn't travel faster than light, so the support will be inside the light cone. And then you take each component of the Fourier analysis of that wave, and you delay that in the direction of that particular time. As you move around the time directions, you're delaying things in different each with its own intrinsic time, then you integrate back. That's what operator means. It means has perfectly good sense, and you write it down with a wave of your hand, just because it is relativistically invariant. Of course, now it has to act on spinors, and it is unique. There is no other animal in the world that has these properties, except, of course, you can always couple the Dirac operator to spinors with something else. And if you do that with spinors with themselves, you get differential forms, and then you get closer to Einstein's equation and so on. But it is a beautiful equation, and once you have the idea you want a retarded operator, there is absolutely no problem. It's unique. You couldn't do anything else. All you can do is vary the constants, k and r. Well, Greg and I played around with this thing, and he's much better than I am at numbers. So we wrote this joint paper in which he gave physically sounding names to this thing. And so this number r, first of all, it turns out, for some reasons, that it has to be quantized. And because some say it has to be multiple of 2 pi r in order to get physically significant answers out. And you work out what is the wavelength of which this basic unit of that quantization, and you end up with a number like 10 to the minus 5 centimeters, which is actually not such a small number. But then later on we dealt with the Einstein equations, and we found another number, another condition, that this k should be related to the cosmological constant, the thing that is supposed to be responsible for the expansion of the universe. And here we got the formulas. This k squared over Planck's constant squared has the scale of a cosmological constant, and you get the number. This is the number we take from experiment, or cosmologists tell us, is 10 to the minus 56, pretty small number. And there is a dimensionless constant in this quantity, which I call mu, which is kr over h. So all very elementary, but nevertheless, there is an equation which is relativistically invariant, depends on 2 parameters, whose orders of magnitude you can make sensible statements about. There's also quantization condition. So it certainly looked like it was worth studying. But I have to say that, well, I took the paper on this stuff slightly, skeptically, and Greg Moore, being a hard-nosed physicist, even more skeptically. But I have to say, I give him his due. He was the one physicist who was sufficiently sympathetic to encourage me to write a joint paper. Most people said, that's nonsense. So it pays to shop around to get a friendly physicist. Now, okay, so I told you about the Dirac operator and about retardation. Now let's go back to our division algebras. I told you about these 4 division algebras. What I'm doing, you see, is I'm illustrating the theme of beauty in mathematics. I'm looking at all the beautiful things that there are in the world, and I'm putting them together. And there aren't that many really unique ones. The SL2R is, a really important group. Number theorists love it. And the division algebras are beautiful things, and they're exceptional groups. So they're marvelous things. So what can we do with this? Well, we can try to extend the Dirac operator to all the 4 division algebras. So instead of taking SL2R, we take SL2C. Then we take the group which we would call SL2H, except it doesn't quite exist because there's no determinant in the quaternions, but you get there are counterparts. The last one is SL2 over the octonions, which even less exists. But these groups can also be interpreted as groups of conformal automorphisms. And underneath, these are respectable groups. Spin 2, I call them spin because I want the right double covering. Spin 2, 1, spin 3, 1, that's Lorentz. Spin 4, 2, spin 6, 2. And these are conformal automorphisms of the interior of the light cone with the appropriate signatures when you factor out by the scalars. These automorphisms, you take the light cone and its base. In an ordinary case, the base would be the circle for the plane. It would be S2 for the 3-dimensional space. But when we go to the next space, we take in a signature 4, 2, so you don't get S4, you get S1 cross S3. Similarly, the last one is S1 cross S4. You wonder why I jumped around in this way, why this sequence of numbers is reasonable. The answer is, look below. These are real forms of the various groups involved, and they're so chosen that they have a torus of maximal dimension, and the dimension of the torus is 1, 2, 3, 4. And no other choice of the signatures would give you that answer. So they're very precisely defined. Now, okay, we've played games, we've looked at beautiful things. I told you that the Dirac operator, thought of as a retarded operator, has some merit. It somehow solves the problem of backwards and forwards things. But actually, it has another property, which I didn't emphasize at the time. That is, this retardation parameter we bring into the Dirac equation, there is a motivation for it, which goes back a long way, and it is, I was very influenced by this. There's a famous textbook in quantum theory book by Bjorken and Drell, which comes in 2 volumes, the first of which is called Quantum Mechanics, and the second of which is called Relativistic Quantum Fields. And in this introduction, which is quite lengthy and worth reading in general, they do discuss the question of what happens with the ultimate nature of space-time. Is it really sensible to think of space-time as a continuum all the way down to anything? And they say, well, most physicists realize that doesn't make much sense. You can't possibly measure anything or see anything when the scales get below the fundamental units with which you can do experiments. So perhaps at that level, space-time is not continuum, but some kind of granular. They call it granular now, pebbles on the beach. And they say, well, if space-time is granular at some scale, then you would have to allow for the fact that differential equations might be retarded. They've got to take time to cross one pebble to the next. It's halfway between the difference equation and the differential equation. So the idea of a retarded equation is closely related to the idea of granularity of matter. What they say in their introduction is twofold. First of all, okay, that may be granular at that scale, but 2 problems are. One is we have no idea what the mathematics of it is. Nobody's developed a theory of these things. Secondly, we don't really need it. Physics is perfectly happy without that. We've solved all the problems of physics. We don't need help from guys working with retarded equations. So they say we'll ignore it in the book. Well, that book was written some years ago. I claim, first of all, we can write down mathematical equations which are retarded and perfectly preserve Lorentz symmetry. I've done it. Secondly, if you look around the world and see whether all is the best of all possible worlds, in Voltaire's words, then you realize there are a few gaps in the present theory. There are problems about the Big Bang. There are problems about cosmological constants. There are problems about inflation. So the present situation in physics is not satisfactory. There are great successes, but there are big gaps. And it's not unreasonable to think that those big gaps represent a big gap in the foundations of physics. One of them might be that you have to take seriously this notion of granularity. So that's what I'm proposing to do. I'm not a physicist, but I'm just doing what the books tell me. So now I have a proposal to make. Okay, I hope the doors are shut and everybody's lips are sealed. I should patent this, but I'm offering it freely to all the world. Proposal that the 4 division algebras, which we numbered, correspond to the 4 fundamental forces of nature: the electromagnetic, the weak, the strong, and gravity. And now I come to mention here Dirac's second mistake. The first mistake was he didn't take seriously this preference for semi-simple groups over solvable groups when he came to do his Dirac equation. His second mistake was to say the following, that all these beautiful things, there was one application of mathematics which failed, and that was the work by Jordan on the octonions, the non-associative algebras. That got nowhere, and not surprising, because non-associative algebras are pretty ugly things, and so you wouldn't expect them to give nice results. So he dismissed the octonions for their lack of beauty, and therefore they were no good. I think that was his mistake. The octonions are beautiful and looked at, it's like the ugly duckling. If you look at it the right way, he's a nice friendly duckling. And if you look at the octonions and see what they generate, all these exceptional groups, and the exceptional groups also produce the beautiful polyhedra results for it, they are beautiful things. You just got to see the beauty. You've got to look at it the right way. So I claim that they are beautiful, and therefore if you can find the use for them in physics, they will give you beautiful physics. And my proposal is a modest one. I'm just proposing that they explain gravity. Right. Einstein did it already, but this is meant to be quantum gravity. So, well, I said work in progress. I don't want to claim any claims. No theorems here. No, just some ideas. The ideas are a bit more that I've explained it here. So at a later stage I may have time to, I was supposed to give a talk to the physicists, which if it's rescheduled, you might hear more on that. Just a couple of points which will pursue this. If you've got 2 points on the hyperbolic plane, we said that they're joined by a unique geodesic. Actually, they're joined by 2 geodesics, if you think of them oriented, one going forward and one going backwards. And if you think of the 2 geodesics as separate, then when you have sort of 3 points, then what you should draw is not the graph, which is the sort of linking diagram of D4, or alternatively the logo of the Mercedes cars, but you should draw this picture here, which is what people nowadays call a ribbon graph. It's a graph has been thickened from just one-dimensional graph to a planar ribbon. And these ribbon graphs have become very popular in recent times for lots of reasons. And notice that why is 2 the important number? 2 is the important number because the orthogonal group in one variable, which you don't think is very interesting, has 2 elements, plus or minus 1. And so that's why there are 2 geodesics, and you get this picture. If you pursue that line of thinking, then you see at once that when you go to the next group up, SL2C, you have a U1 family of geodesics, because you get really a complex curve, a complex Riemann surface, and you get the familiar pair of pants. And if you do the next one up, SL2H, what's really in quotation mark, you get an SP1 family of geodesics, which replace the circles by 3 spheres. You get a 4-manifold picture of that. And the next one up will be an 8-dimensional manifold. So each of these 4 division algebras gives rise to a pair of pants which are more and more expensive. Now that I just drew the simple graph of the linking diagram of D4. I say it's the Mercedes cars. I think I think I could sub-patent it to Mercedes, or we could get sponsorship to get the Mercedes cars to support work on quantum gravity. These days you have to look around for sponsorship quite a long way. The Feynman graph is, of course, what physicists have got by gluing together these elementary graphs and making more complicated diagrams. And now they know in string theory they do it with these Riemann surfaces. That's the merit of the Riemann surfaces string theory was that you got rid of the singularities which were at the nodes of the one-dimensional graph. The nodes that got smoothed out, you get a nice Riemann surface. Well, the same thing applies, of course, if you take dimensions 4 and 8. So why stop at 2? Now, we know that there are 4 forces. There are 4 division algebras. You can play these games all 4. The rest of it is obvious corollary. Detail left to the reader. I started talking about beauty and truth and all that, and I think I gave you a few quotations from other people, and I think I'd like to end with a quotation of my own. I'm not a poet, but I wrote one poem in my life, and this is it. Well, I didn't really write it as a poem. When the IHES was celebrating some anniversary, it asked me and other people to contribute a little passage. And I contributed a short passage and I think it really sounds more like poetry than prose, and it exists both in an English version and in a French version, if you prefer French poetry. And so here it is. I call it dreams. In the broad light of day, mathematicians check their equations and their proofs, leaving no stone unturned in their search for rigour. But at night, under the full moon, they dream. They float away among the stars and wonder at the miracle of the heavens. They are inspired. Without dreams, there is no art, no mathematics, no life. Thank you.